I'm presenting about the special affine Fourier transform for signals in space-time algebra. My name is Eckhard from International Christian University in Tokyo, and it's my honor to present at the Engage workshop at CGI 2021 in Geneva. First of all, I will make some acknowledgements. I quote from the Bible, King David, "What is man that you are mindful of him, and the Son of Man that you visit him? For you have made him a little lower than the angels, and you have crowned him with glory and honor." I thank my family, the members of the Engage Workshop Advisory Board, and the organizers of CGI. This research is under the Creative Peace license. I dedicate this work to the 70-year-old London pastor John Sherbert, who was arrested on the 23rd of April 2021 by police in Uxbridge, London, for preaching publicly about these verses in Genesis. So God created man in his own image. In the image of God he created him, male and female he created them. Then God blessed them, and God said to them, "Be fruitful and multiply. Fill the earth and subdue it. Have dominion over the fish of the sea, over the birds of the air, and over every living thing that moves on the earth." I first give an introduction, then explain a little bit about space-time algebra and the space-time Fourier transform. Then I'll introduce and explain the special affine space-time Fourier transform and give conclusions and references. This slide explains the history from Fourier transforms to special affine space-time Fourier transforms. In signal processing, in 1994, J.T. Sheridan as other introduced the special affine Fourier transforms. In the meantime, also hypercomplex quaternion and Clifford Fourier transforms have been introduced. Furthermore, one of these is a space-time Fourier transform on signals defined in Minkowski space-time R31, ranging in the geometric Clifford algebra of space-time STA. It has many applications for electromagnetic waves and newly also maybe to space-time crystallography. And it is of interest to quantum bit computations and quantum computing as well. This is steerable split of quaternions that becomes in space-time algebra the space-time split defined by the time vector and its dual trivector, the volume element. It splits any space-time signal into two wave packages traveling to the left and right, which are classical solutions of the relativistic wave. The space-time of Einstein's special relativity is a 4D non-Euclidean quadratic space, R31, with orthonormal basis Et for time, E1, E2, E3 for x, y, z. The time vector, the space volume, and the hyperspace volume subalgebra of space-time algebra is isomorphic to quaternions. Each of the three elements squares to -1 and they mutually intercommute. The space-time split uses the time vector and the space volume on the left and the right of the element to compute m plus minus as 1/2 m plus minus ETM I3. Every multivector is a sum of m plus m minus parts, and we have this very interesting commutation relationship here. We can define a multivector norm, which is basically the sum of all the coefficients of a multivector squared. And in the multivector norm, we have this Pythagorean identity for the multivector plus and minus parts of the split and their norms. The space-time Fourier transform can be defined by taking a space-time signal, which as the domain has the Minkowski space argument x, and the range is in the space-time algebra itself. And we have two kernel factors, one on the left side with the time vector and the exponent, then time times frequency, and on the right side we have the volume element and the exponent and the inner product of the space vector and the frequency vector. The SFT has very interesting properties. There is an inverse, there is anisotropic scaling, then we have a Rayleigh-Parseval energy theorem, and we have formulas for the partial derivatives the SFT of the partial derivatives. There is a directional uncertainty principle for the space-time Fourier transform. We have two directions in Minkowski space, C and D, and we compute the variance in the position space in the direction C and the variance in the frequency spectrum in the direction D. And the product is limited by 2 pi to the power of 4 divided by 4. And in squared brackets, we have the factor inner product of the vectors C and D with a minus sign times the right traveling wave packet energy, and the inner product of C with D with a plus sign times the energy of the left traveling wave packet squared. Now we will define the special affine space-time Fourier transform. First of all, we need to define special affine phase space transformations with matrices A, B, C, D, with small a, b, c, d and capital A, B, C, D. They both have unit determinants, which guarantees lossless area and power preserving transformations. And then we have translation vectors Mn, or these vectors capital M, capital N, which are vectors in R3. Using these coefficients, we can define the left and right kernel factors as you see here. The left one, small k, depends on time and time frequency. And on the right side, in the definition, in the exponent, we have, like in the space-time Fourier transform, et, the time vector, and we have the right factor that depends on the position vector and the frequency vector. And on the right side, we have in the exponent I3 the space volume. We simply multiply the signal in the definition of the special affine space-time Fourier transform with the left kernel factor and right kernel factor, and then we integrate over Minkowski space in 4 dimensions. This super transform unifies the space-time Fourier transform, a linear canonical transformation generalization of the SFT, a generalization of the SFT to a fraction Fourier transform, a length transformation, a free space propagation transformation, and a magnification transformation version of the space-time Fourier transform. Now we'll present some properties of the special affine space-time Fourier transform. First is that we can compute the special affine SFT using the SFT itself. We simply take the signal f of x, multiply it with 2 phase factors from the left and the right. Then we scale the frequency argument of its space-time Fourier transform, and we multiply by further phase factors from the left and the right. So basically, scaling and multiplication with phase factors allows us to compute the special affine SFT using the SFT. Interesting properties are left linearity with respect to multi-vector coefficients that commute with the time vector et, as given here alpha, and right linear with respect to coefficients that compute with the space volume element I3, so they exclude the time vector beta here, as written out here. And you see here the formula for the left linearity having alpha coefficients, and the formula for the right linearity having beta coefficients. Then we have that if the limit of the magnitude of the frequency goes to 0, then the norm of the special affine SFT also goes to 0. Finally, the special affine space-time Fourier transform is uniformly continuous in Minkowski space. Further important properties are the space-time position shift k and modulation. So we can shift the argument of the signal from x to x minus k. That's the same like computing the special affine SFT of the signal at a shifted position in frequency space and multiply with phase factors from the left and the right. Furthermore, there is a space-time frequency modulation with a frequency vector in 4 dimensions mu, and we can multiply the signal with the modulation phase factors from the left and the right, indicated in blue. And then we do the SASFT, and we get the SASFT of the original signal at a shifted position in frequency space times phase factors. We also have an inverse formula, so we take the SASFT of the signal and multiply it with the principal reverse of the left kernel factor and the right kernel factor and integrate over the four-dimensional frequency space, and we get back to the original signal. Furthermore, in position space and frequency space, the signal energies are the same. So if we compute the energy of the signal after the SASFT is performed, the value has not changed, the energy is preserved. We also have a formula for partial derivatives, here for example for d by dt of the signal plus a linear term in t times the signal. And if we compute the integral over space, we get the integral over the square of the SASFT multiplied by the frequency component in the time direction squared. And the same happens in analogy if you replace the partial derivative with respect to t by the derivative with respect to x by z, and then we take the corresponding frequency components in the x by z directions. Now we will present the uncertainty principle for the special affine SFT. We have an uncertainty principle for the SASFT. The directional uncertainty principle for the SASFT expresses that we can compute the variance of the signal in the direction of a fixed vector c and the variance of the SASFT in the direction of a fixed frequency vector d, and the product is greater or equal 1/4, the inner product of the two vectors is a minus sign, times the right traveling part of the signal energy, plus the inner product is the plus sign of the two vectors times the energy of the left traveling part of the signal squared. It says that we have a limit to the simultaneous measurement of space-time position and space-time frequency. Finally, we have the uncertainty principle for coordinate directions. These coordinate directions are time direction and x, y, z, given by 1, 2, 3. So we compute for a coordinate in position space that can be time x, y, or z, the variance, and for another coordinate in the frequency space using the SASFT, the variance, and that's greater or equal the Kronecker delta function of the two coordinates times beta squared f squared. And beta is one of the coefficients of the phase transformations we have introduced at the beginning. This means there is a measurement limit on variances in time and frequency, as well as the XYZ coordinates and their corresponding spatial frequencies. We have given background on the space-time algebra, then reviewed the space-time Fourier transform SFT and introduced the special affine Fourier space-time Fourier transform SASFT. This lifts the special affine Fourier transform to a high-dimensional geometric algebra integral transform. And we expect that there are many applications, both theoretically and in applied research, of this new type of hypercomplex transform in physics, even up to feature preprocessing for deep learning, etc. Here you see the works of Abe and Sheridan and other literature, which is helpful to understand today's presentation. In particular, the last reference shows a corresponding work for the quaternion Fourier transform. It's now time for questions. Solidaire Gloria, vielen Dank, merci vielmal, merci beaucoup. Thank you very much. どうもありがとう。